So in this problem we're going to draw a shear and moment diagram for the beam shown below. We have a 6-meter beam with a uniform distributed load on it, and we have a wall at the left end and a roller 4 meters down the wall. E and I are constant in this problem. So the first thing we're going to do is draw a free body diagram. And it's going to be extremely important here because we are going to need to know if this beam is determinate or indeterminate. So over at the left end there we've got 3 forces. We've got 2 perpendicular forces which represent the complete translational restraint of the wall. And we have a moment that I've called M1 which represents the rotational restraint at the wall. We've got over at the roller, with the roller removed, it had a vertical restraint, and so that's represented by load F3. We're going to end up doing 2 solution procedures here. We're going to do solution by the second order beam, and we're also going to do indeterminate superposition. So starting with the second order beam. The second order beam equation tells us that the curvature of the beam, the second derivative of V, where V is the transverse displacement of the beam, is directly proportional to the moment divided by EI. So what we're going to do is we need to find the internal moment inside this beam. So what I'm going to do is I'm going to cut this beam open at a distance x. I like to think of this as the blue saw at x. So on the left hand side you see the wall forces, the 3 red arrows. Again, we have a distance x. Exposed at the cut are the 3 internal forces: moment, axial, and shear. These follow our consistent sign convention. On the other side of the cut, left over, I have 4 minus x. I have the 2-meter overhang. I have the equal and opposite forces internal to the beam. And so what I'm really interested in is finding the moment inside that beam. So the fastest way to do that is to go ahead and sum moments at the cut. I'm going to choose to use the right side free body diagram because I'm going to choose to solve for the moment in terms of only a single red arrow. In this case it's going to be in terms of F3. So if I sum moments right at the cut, right there, I end up with an equation that has m of x in it. I've got minus F3 times 4 minus x. And then what we've done is created a statically equivalent point load. And the value of that point load is going to be 2 times 6 minus x. So you see the magnitude of it. The centroid is going to be right in the middle of that uniform load, so it's going to have a lever arm of m minus 6 minus x over 2. So if we go ahead and just start solving for m of x, I'm going to do just a little bit of manipulation on that to end up with an equation. Again, a second order equation. I've got x squared, I've got a quantity multiplied by x, and then I have a constant term. So for the second order beam equation, I'm going to need to apply my boundary conditions. So my boundary conditions for this beam involve, first of all, setting up a coordinate system. So I'm going to set up the x-axis going left to right. On the beam in the transverse direction, right there, that is v of x. So my boundary conditions involve the wall and also the roller. Kinematically, I have known displacements. I've got the transverse deflection at the wall is equal to 0. I also know that the slope, or the first derivative of v with respect to x, is equal to 0. And then I have another boundary condition out at the roller, and I would describe that as v at 4 equals 0. So again, in this indeterminate beam, it turns out that I have 3 boundary conditions. So let's go ahead and put our m of x that we've got right up here. We're going to just go ahead and put that right in the second order beam equation. So if I just rewrite that, I've got the second derivative, or the curvature, is directly proportional to the moment divided by EI. The x dependence on E and I goes away, as this is as E and I are constants. So what I'm going to do is separate and integrate, and so I'm going to end up with an equation which is based on the slope of the beam. So what's happened, right? I've raised the exponent to 3 and divided by the new exponent, and I've just done that 3 times. And what's now joined the party is a constant of integration. I've called it C1. And at this point we have a boundary condition that we can apply. I know that the slope at the left end is equal to 0. So what I'm going to do is I'm going to take and apply x equals 0 in all these equations right there, and that's going to end up zeroing out quite a few terms. So you see the application of 0. I know that the slope at 0 equals 0, again looking back at our boundary condition. So I end up with an equation that looks like, like 0 equals 0 plus 0 plus C1, giving me the fact that C1 equals 0. So what we've just done is that term right there equals 0. So then what I'm going to do is integrate this. I'm going to integrate this one more time. So all my third order went to fourth order, second went to third order, my linear term went squared, and now I have another constant of integration. I'm going to apply my boundary condition v at 0 equals 0. Again, right here I've already applied this one. I'm now going to apply that boundary condition. That's going to give me the ability to solve for C2, and we see very nicely that C2 equals 0. And so now my equation for v of x looks like this. I've solved for both constants. They've happened to be 0. And so this is the transverse deflection profile, but we still have an unknown. We have a red F3, right? That's the roller force that's sitting in our free body diagram. But I've got one more boundary condition. I'm going to plug in the fact that at x equals 4, I know what that transverse deflection is. That's going to be 0. And so my math then comes out such that I can solve for F3. So that's all I've done here, is I've just simplified the math a little bit, grouped F3 on one side, and numerically I've come up with an answer for F3, which is going to be positive 8.5, and that relates back to my free body diagram where I had F3 going in the upwards direction. So I now have F3 defined as 8.5 kilonewtons up.